So, dear friends, dear participants, we're here again in our webinar meeting of our colloquia on portable pXRF fluorescence organized by the European Academy of Science and Arts, STEMAC expert group, STEM in Arts and Culture, and the global pXRF network. For our academy, this is a follow-up of a specialized section of the successful colloquia, Arts Meets Science, for the last 4 years, actually, and a further activity of STEM in Arts and Culture expert group. Myself and Michaela wish to express our gratitude to Keelie and Dolis Kulida from the Academy for their immense technical help in organizing this colloquia. Today we have two speakers, Dr. Kyle Freund, a Cultural Research Program Lead in Idaho National University, and Dr. Ellery Frahm from the Department of Anthropology and Council of Archaeological Studies at Yale University. I think the first speaker will be Ellery. Is it right, Michaela?
Yes.
Okay, so you can introduce Ellery Frahm, and then I will introduce Kyle Freund.
Yes, thank you. I'm really excited to have Ellery Frahm with us today. He holds a bachelor degree in physics and a master in interdisciplinary archaeological studies, and has a PhD from the Department of Anthropology at the University of Minnesota. Since 2017, he teaches and researches at Yale University as a leading scientist and was promoted, as far as I could see, this year to senior research scientist as a research professor. So congratulations for that, especially in the current climate. That's really impressive. He's also the director of the Yale Initiative for the Study of Ancient Pyrotechnology and a curatorial affiliate at the Anthropology Division at the Yale Peabody Museum, which I'm excited about now that I'm working at a museum as well. And he's co-editor-in-chief of the Journal of Archaeological Science Reports. His studies focus on material characterization to make the unobservable behavior visible and study the human interaction with natural resources and their environment. He has an incredible record of publications with contributions covering a time span of almost 500,000 years and 5 different continents, even if his research focuses on Southwest Asia, the Near East, and the South Caucasus. His studies are ranging from a variety of materials with a focus of obsidian, but also pottery, and includes method studies as well as best practice, discussions, and guidelines, such as his recent publication of 2024. As part of best practices, many of us know that proper standard sets are key so we get high quality data. So I'm really excited for Ellery to talk about all kind of standard sets he has developed, and I would love to hand over and have you started with your presentation.
Thank you very much for that wonderful introduction. Yes, so I've been asked to talk about essentially one of those scenarios where you realize if something is going to get done, I guess I'm going to have to do it myself. Us academics are very good making work for ourselves. So this is one such story about making work for myself, but with hopefully a benefit not only for my own students but the broader community. So, I mean, this was the problem I was facing. I mean, when you're a researcher doing your own thing, and you have stable access to an instrument, and you're just going back and forth into the field, you can be pretty happy that your data are compatible with each other for the most part. But when you start getting students or colleagues and coworkers who are working all around the world, or you have students that cannot bring an instrument to the country, they have to use the instruments in country, how do we get all of those data sets to agree? And so these were problems that I had started thinking about back when I was a Marie Curie fellow at Sheffield on what was called the Narnia Project. And I was on the pXRF kind of work package that had two basic written remits. One is work where we couldn't work before, and two, try to answer what we couldn't answer before. And then there was kind of a third unwritten thing that has become more explicit in what I tried to do, and that's include and enable those who weren't before. And a lot of what was mentioned in my, again, the very kind introduction was kind of spelled out here, in that it's not good enough, or it shouldn't be the role of experts to tell people, hey, you're doing it wrong. I know how to do it right, full stop. Or, you shouldn't be using that, or that sort of thing. The role of an expert can pivot when a technology suddenly becomes a lot more available to imparting and freely giving the knowledge and tools to do work correctly, to help people do it the right way, rather than just telling them they're doing it the wrong way. And before diving into the sets themselves, I did want to start with kind of a let's get all on the same page, especially if there are people who don't attend every one of these talks, or may have some ideas. And towards the end, if you disagree with these propositions, anyone, we can talk about this in the later in the question and answer after Kyle talks. But just to lay some foundations. So I'm going to start with proposition one. These are all kind of what I call fifth generation pXRF instruments. They're more alike than different. They're all very good. Going along with that is really, in terms of hardware, they're almost all the same now. Many of them have the same parts from the same manufacturers. Really what we're dealing with is just all the software side of things that differs between the different models these days. And that can include everything from the user interface, how you deal with quantification, and then things like calibration, like we're talking today. Proposition two, early adopters and testers, by definition, used outdated models. Okay. It's a bit like complaining that iPhones can't take photographs because you're using an iPhone 1 instead of an iPhone 17. So kind of proposition 2B then is that any assessments based on those instruments are also outdated as well. Proposition 3 is analyzing ceramics, archaeological ceramics by pXRF can be valid, reliable, and behaviorally insightful. In a bit of self-promotion. As an example of this that I know well, let's put it that way, is this paper from 2018 that was kind of a long time coming. Not to get too deeply into it, but this shows an example of how I was able to pull out difference between imports versus locally made ceramics that stylistically are the same, but chemically it was clear one's locally made versus one that's imported. And then proposition 4 is, yes, ceramics are mixtures. This would be something Lee would remind us of. But we can adjust for this. And again, in that same paper, I had done this experimentally, showed that, yes, there are effects from different tempers in different sizes and abundances, but they behave in predictable ways that we can account for. So this is just, not to get into the details, but a combination of experimental clay rods that were made for me at Democritus in Athens with 2 different clays and 2 different tempers. And so what you see is, yeah, as you add more quartz temper, the silica goes up. And as you add more shell temper, the calcium goes up. And as you add more temper, trace elements essentially get diluted, right? Because everything has to add up to 100%. So trace elements have to go down as you add more other stuff to the ceramic. But something simple like ratios that can get rid of that dilution effect as long as it's systematic, can pull out those two different clay sources very well. And then all of this kind of has to deal with the fact that, believe it or not, we are not the primary market for pXRF. No one really makes instruments for archaeologists. They're made for industrial applications, and we have to kind of leverage those strengths. And so the good news is that a lot of those applications are analogous to what we're interested in. Soil chemistry. Humans are we're great polluters, no matter what time of history we're talking about. People measuring ores for geological purposes. They're interested in many of the same things we are. And metals. And what was eventually appreciated was that because there was, a big market in, say, analyzing metals in junkyards, there were great calibrations here, and that metals were better analyzed in a place like this than in a museum like this. Again, not anything other than essentially the software, right? The hardware is fine. There's other issues like corrosion and treatment, and that these are not flat pieces of metal. But it's just very different to try and figure out what statues like these are made out of compared to what your scrap metal is worth. And so this was recognized back more than 10 years ago, where, again, there was a collaboration that came up with what's called the CHARM set. These are based on copper alloys that are common in certain segments of historical copper alloys. It's not perfect when it comes to China and so forth, but it was a first attempt to come up with a way to have shared metal standards amongst particularly museums and heritage organizations trying to analyze their copper alloys. Now, there's some problems or challenges with this approach. In this case, the approach was they commissioned these sets to be made, these metal alloys. And what happens is you ended up with sets that were like almost 8,000 euro. Who could afford that? Established labs. You're not going to have any master's students just, can we pick up one of these sets? And again, the result is what we have to think about, or I think about in terms of essentially the impact of doing this, is it doesn't change the status quo. The good established labs who could do this work already are going to be the ones with these sets. And then before we move on, there were these, I want to show you what analyzing a standard looks like, if you're going to call it a standard. So this is an example of geological materials standards from the United States Geological Survey that were available for many, many years until our government decided everything had to make money. And so most of them aren't available anymore, and they're about 5 or 6 times as expensive as they used to be. They used to be like 30 or 40 bucks for each powder, and now it's like 200 or 300 or something like that. But this is a good way to show what a standard looks like, what a reference should look like. And so just as one example, for one of the shale standards, this Devonian, Ohio shale standard they made, SDO1, they published a lot of analytical work. And what you see here are the results from many, many different labs. You'll see sometimes even 26 different labs analyze these powders. The results were combined, statistically analyzed, kind of consensus values were come up with, outliers were tossed. This is how you do good standard work. This is really, really well done. And then they published, what every lab did with every technique, super transparent, really rigorously done. And that's why people liked these USGS standards. So what then did we have for archaeology? And like I said, these companies rarely do things for archaeologists themselves. Again, this part kind of falls on us to do. So what was out there? Again, as I started, especially accumulating students working around the world, what are our options? And so one of them that was kind of first used by folks was this, what Bruker sold as their ceramic/mudrock calibration. You can see here how they're saying, this is Mother Earth's ceramic. This is what you should use. And there were some problems with it. All of the materials, or almost all of them, something like 90% of the rocks that they used for this calibration were derived from these deep drill cores in Texas with hydrocarbon-rich shales, which means it is not a silica shale or slate calibration that is what would weather into ceramics. It's an oil shale calibration. It is full with all these carbonate rocks and all these deep cores. So that's problem one. Problem two, I just showed you, a standard where sometimes 24 labs had done the analyses to come up with really accurate measurements. Only one lab was used to generate measurements on those oil shale pieces. And the result was not great. If the measurements worked, they would all fall along that dashed green line, not be the red best fit line with really bad R-squares. So it wasn't a surprise. Another group out of Georgia with Hunt and co-authors suggested a clay sediment analysis or standards. So they suggested 33 existing standards, kind of like that Devonian shale from the USGS. Another problem, 17 were still available. You're back up to 5,000 euro again. And the other 16 weren't available anymore. You couldn't buy them. They're old. So who has them? Established labs. It just went to reinforce the status quo yet again, kind of under the guise of, we're doing something more transparent. The other problem is they evaluated the calibration using the standards in their calibration, which is the same as using one half of your ruler to measure how well the other half of your ruler works. So not great. So again, this was the kind of thing where if I want something that I'm confident in for my students to use and for colleagues to use, I guess I got to do it myself. And so this wasn't, this is something I knew how to do. This is baby me in grad school, circa 2001, working on an electron microprobe. I did develop standards for that back in grad school. I had made obsidian calibration sets. Again, version 1.0 of this was while I was at Sheffield working on the Narnia project. And now this is version 2.0, the pyro sets that are transparent. And I'm at Yale, home of the first XRF analyses of archaeological ceramics. So what better place to do this sort of work? So the next step was deciding what should the reference materials be? What should I use instead of, say, random grab pieces from companies' deep oil shale cores? And so again, I looked to what have other certifying agencies used. This is from the National Bureau of Standards, which is now NIST, the National Institutes for Standards and Technology. BRICC clay is what would be a major standard to use, especially for neutron activation analysis of ceramics. And indeed, when it became clear and NAA was starting to get going, NAA experts like Garman Harbottle, working at Brookhaven National Laboratory, came up with an Ohio red clay as an archaeological clay standard to use for NAA. NAA is a little straightforward where you can get away with having just one or two reference standards, but this was what was used there. And one thing that Garman Harbottle had done is look at historical bricks as essentially reservoirs and archives of historical clay deposits, especially clay deposits that have been exploited or are no longer accessible, or they've been paved over or something like that. And so, he showed this is a good resource to use. And so, together with a bunch of students as a COVID era project, we went ahead and started compiling historical bricks from all across the US. And these are great because they have right on them who made them. And it turns out there's lots of really enthusiastic brick collectors out there who've compiled all sorts of information about, for example, which of those logo styles was made in what years. So you can really find good, accessible, reproducible archives of past clay deposits down to a couple years span, and on a map by using historical bricks. And that seemed like, if you're going to use some sort of clays and you want the most reproducibility of what you've done and the most transparency of what you've done, this seemed quite the way to do it. And again, what's great is there's records for how they were made. We know that they weren't altered. They didn't add temper, all these sorts of things. And you can go and access these today. In fact, this is about 4 miles that way in North Haven, Connecticut, where there was a ton of brick production. So these are some of the bricks that I had mailed to me. My postal carrier is thanked in the brick paper for bringing me hundreds of pounds of bricks during COVID. But we knew where all of these came from. We had geological maps. We did tests on intra-brick homogeneity, making sure that if we sectioned these, that one part of the brick would be uniform as the other part of the brick. Anything that failed that, we tossed. And then we also did things like inter-brick homogeneity. So we got this is an example where 4 bricks from the same brickyard. Again, we know they're made in the same time frame because they've got the same style of stamp. And their coefficient of variation amongst them is like an order of magnitude or better than if you just randomly pulled out four bricks. So it fit all the assumptions of the provenance postulate. We did all our due diligence, and an important thing we also did was make sure that we were capturing real archaeological ceramic variability, because there are things out there that geologists will call clay that you couldn't make a pot out of. And the same thing with those oil shales is, technically they're comprised of metamorphosed clay-sized particles, and some of them probably have some clays in them, but they also have a bunch of other minerals or so many carbonates in them you'd never make anything out of them. A pot would not work. So we pulled together more than 20,000 analyses from the literature to get a range of, what should these elements look like, and are we capturing this range as best we can within some bricks. We did pretty good, but we thought we should implement or supplement rather the collection with, I think we added about 5 geological samples. This is, again, some examples of very famous localities where we can, in the paper, we've got GPS coordinates about where these quarries are. Things like the Monson Slate. Again, these are very famous historical deposits. All the slate roofs in Maine came out of this one pit in the ground. And so good records, good reproducibility, and gave us a little more variation in the elements we were interested in. So those that passed all our tests of being homogeneous within them, not just being a duplicate of some other composition we already have, we sent off to multiple labs by multiple techniques. So we did some work in-house, and then we sent out some WDXRF, we did some ICP-MS, two different labs, neutron activation analysis. And while those labs were chugging away, again, during COVID at getting us, helping us determine some consensus values, so we weren't just relying on our own in-house measurements. I was busy cutting all these bricks into those are about 3 centimeter diameter, something like that. Cutting the bricks up into these chunks, these cookies, whatever you want to call them, and then mounting them in epoxy so they're nice and safe. And then brought them home and put my kids to work with washing and grinding flat surfaces and labeling them all. And in the end was 10 matched sets that look like this. So on the left portion are those bricks and the supplementary geological materials. And then you'll see 2 other things there. There's a fused disc and of silica, and then one that has a USGS name by it. In Obsidian, there's a couple different kind of routinely used accuracy checks. RGM 1 and 2 are the most common for XRF. Ceramics, we couldn't find that anyone has come to that kind of same consensus on, hey, we should use specimen X. So this is probably, this SBC is Brush Creek Shale. It's probably one of the best characterized shales on the planet. 75 labs participated. As I said, unfortunately, this material I don't believe is available anymore, and it became unavailable during the course of this testing. But I had a big enough jar to be able to create 10 fused blocks. Since Kyle's talking to us next, the only change was water was driven out. We could measure the water loss before and after firing. And if something, let's say it was 10%, let's round it to 10%. You had to round, every other element had to go up 10% relative in order to get a good thing. And so all the calculations for that are in the BRICC paper. But this way you avoid sending around strange powders in the mail, which causes problems. So I fused those, and then there was that fused silica blank. This is like optical grade, super pure silica that when you analyze it, you should get nothing but silica. So again, it's another check to make sure that, if you measure it and you're getting really anything other than silica, then you need to kind of tweak your calibration some. And then to add to that, just everything got published. We published all our values. When we had geological maps, they're in there. When we've got GPS coordinates, they're in there. Just, all the measurements are in there. Everything we can, so that, in theory, one could go out and make your own version of this. And we made them free to borrow. So we don't sell them. Eventually, there's enough demand that I might make some smaller chips from the bricks that maybe people can just keep or something like that. But there's very high demand. I've got a wait list, as Kyle knows. But Kyle, I bothered people this morning to, hey, if you're done with this, please send them back. We got a wait list going. So everything's out there for it, and then all the students who were helped during that COVID project are on there. And again, to wrap it up, the goal of this is to make pXRF like a lot of other technology in archaeology. So these are actual books, believe it or not, that are out there. You youthful people might not believe this, but and you'll see that they often have the same person there. It's all about hey, here's the right way to use computers in the field, and now we just take all this for granted with much more powerful computers in the field than those people were ever writing about, and they're super routine. And that's again my overall philosophy as an expert is. This is from 1983. It was an ad that they put a computer attached to the XRF, and this is going to change everything. And I'm sure there were totally analog experts out there going like, "Oh, computers! I want I want to measure it out on graph paper. So do it all manually, the right way." But to make that change so that it's totally as routine as it can be, and just a great tool in our arsenal. And so that's the quick version of the BRICC story. And I think I'll end there. And I'm happy after Kyle, which I'm eager to hear what he has to say. Happy to answer questions about these afterwards.
Thank you very much. That was amazing. And I had my pen out.
Good.
That's for later. Now, Ioannis, you're up. But you're muted. Sorry.
Okay. It was very essential because of the calibration issue, which everybody talks, but that was a very deeply made, and thoughtfully made work that we can discuss, I suppose, at the end. Now we can go on to the next speaker. I would like to introduce Dr. Kyle Freund, Adjunct Assistant Professor at State University of Nevada, Las Vegas. Kyle is also a Principal Investigator at Far Western and member of the company's X-ray Fluorescence Laboratory. Far Western Anthropological Research Group is a major U.S. cultural resource management firm specializing in archaeology and environmental compliance, and his specializations include lithic analysis, obsidian sourcing, GIS and special statistics, and field survey. Prior to joining Far Western, Keelie served as an assistant professor of anthropology and Back Atlantic endowed teaching chair at Indian River State College in Pierce, and he holds a PhD from McMaster University in Canada and an MA from the University of South Florida, and a BA from the University of Florida as well. Keelie's regional specializations span from the Old and New Worlds, including island and coastal contexts of the Mediterranean and Florida Peninsula, as well as desert environments of the US, Great Basin, and Arizona. He has spearheaded a variety of major research initiatives that demonstrate his ability to effectively oversee project development, execution, and advisory services related to cultural resource management and compliance. Keelie's research is published in a wide variety of peer-reviewed journals, books, and technical reports, and he has presented his work at over 50 venues in more than 10 countries. He has also served on numerous committees and boards, including within the Register of Professional Archaeologists, the Society for the American Archaeology, the International Association of Obsidian Studies, and the Society for Archaeological Sciences. So, dear Dr. Freund, the online podium is yours.
Well, thank you very much for that kind introduction here. I'm going to share my screen. It's going. There we go. Okay. Well, again, thank you very much for the invitation to speak to you all today. Before I get too far, I just want to say that this work represents the contributions of multiple people including Jeremias Pink, Josh Clements, Claire Cathers, Chris Woodbury, and members of the Shoshone-Bannock Tribes Heritage Tribal Office. I also want to say, I very much enjoyed Ellery's talk. Yeah, and as he mentioned, I'm on the waiting list here. If you're interested, make sure you reach out soon. Yeah, I definitely look forward to seeing how the BRICC set will impact our data output. So this study explores the impact of firing on the elemental composition of clays using XRF. So I'll begin with just an outline of what I'll talk about right now. I'll talk briefly about ceramic analysis with XRF. I'll provide a background to the study area, talk about my methods, clay collection, XRF analysis, and statistical comparisons. Talk about the results, obviously, the macroscopic changes we observed in our fired clay tablets, changes in mass, changes in elemental composition, and the impact of temper on elemental readings. I have a discussion trying to explain the phenomena that we observed and its archaeological relevance, and hopefully end with some conclusions and future directions. So this research focuses on the use of XRF spectrometry in the analysis of ceramic artifacts, which is typically centered on identifying distinct geochemical groups within an assemblage. The existence of distinct geochemical groups implies the presence of separate paste recipes. That in many cases indicates the use of different clay sources. Building on that, the matching of archaeological ceramic sherds directly to georeferenced clay sources has the ability to greatly expand the range of relevant research questions archaeologists are capable of addressing, which is really where this work has the most relevance. This is an inherently difficult process because clay sources are often found in fluvial environments that cover wide geographic areas. The collection of a comprehensive database of clay sources is also a labor-intensive process that may not actually represent the available clay sources in the ancient past. Moreover, for sourcing to be possible, clay sources must be more compositionally distinct from each other than they are internally variable, the so-called provenance postulate. Another issue is that the comparison of raw clay samples with ceramics that contain both clay and temper is not a one-to-one comparison, and the validity of these comparisons is context-dependent based on the mineralogy and volume of the temper. That said, there's great promise in continued ceramic studies with XRF due to its ability to quickly and non-destructively analyze artifacts. And I think these aren't issues I need to get into too much. I think I'm preaching to the choir here in a lot of ways, maybe. So some research questions that are driving the work here. What is the impact of firing on the elemental composition of clays with specific reference to XRF analyses? Should raw clays be fired before comparing them with ceramic artifacts? What is the impact of sand tempering on XRF measurements on ceramics? And while there's a robust literature out there on reconstructing initial firing temperatures and the impact of firing on the mineralogical structure of clays and ceramics, and a limited number of associated studies on the impact of firing on elements commonly measured using techniques like NAA primarily, such studies have not been directly applied to XRF. So for example, COLLOQUIUM et al. 1988 state that it's generally safer to compare a clay with ceramics after it has been purified and fired than it is to compare it raw. Cogswell et al. 1996 demonstrate no effect of firing on elemental concentrations for 33 elements commonly measured with NAA. And in a study by Vilke et al. 2016, I think Dept is here, the impact of firing on XRF attenuation rates, so-called matrix effects, have been mentioned as a potential factor impacting comparisons between geological clays and fired ceramics. This is yet to be fully tested. Right. So turning our attention to the study area and where I specifically work at the Idaho National Laboratory, or INL. Here it is here in Idaho. INL is part of the U.S. National Laboratory System, which is overseen by the U.S. Department of Energy for scientific and technological research. The INL Cultural Resource Management Office is responsible for managing compliance with applicable cultural resource laws and regulations on the roughly 900 square miles of property shown here, known as the INL site. The INL CRMO runs an XRF laboratory for the analysis of archaeological materials, which I oversee. The INL site is part of Eastern Snake River Plain, an elongate low relief topographic depression that extends from the Wyoming border westward, following the track of the Yellowstone volcanic hotspot. It's one of the most prominent geomorphic features of eastern Idaho, being underlain by a thick sequence of tertiary and quaternary rhyolitic and basaltic volcanic rocks. Lands of the INL site are within the core area of the Pioneer Basin, a closed drainage system fed by montane watersheds to the north. Three of the largest streams, the Big Lost River, the Little Lost River, and Birch Creek, converge on the INL site in a series of playas and sinks, where they disappear below ground into the Snake River aquifer. These natural features are remnants of Lake Terraton, a Pleistocene lake that once covered much of the northern INL site, but is now dry. You can see that here we've got the Big Lost River, Little Lost, and Birch Creek, and here's a reconstruction of what Lake Terraton would have looked like. To the south, three volcanic domes rise abruptly from a rolling plain of superimposed basalt flows extruded from low-relief shield volcanoes. Big Southern Butte is located 10 miles south of the Big Lost River, just outside the INL site, and the twin buttes, East Butte and Middle Butte, are located within the INL site near the route linking present-day Arco and Idaho Falls. So here's some pictures of what the kind of environment looks like here. You can see East Butte and Middle Butte, and shown here is one of the few times that the Big Lost River flows. There's a dam upstream that limits its flow for most times of the year. Here we are collecting some clay on the right. So drawing on previous soil surveys and in collaboration with the Shoshone-Bannock tribes, 19 potentially clay-rich collection localities on the INL were identified on the Big Lost River floodplain. The Lost River sinks in the Lake Terraton Basin. Using a 3 1/4 inch bucket auger or trowel, clay samples were collected from 17 locations across the INL. Samples were not collected from 3 sampling locales determined to be insufficiently rich in clay. 2 samples were collected within 300 meters of the same location. After collection, dry clay from each collection locality was crushed and formed into 3 domino-sized tablets through the addition of water. A total of 51 clay tablets were created. For sampling locales with associated sand deposits, which were 5, 3 additional tablets were created at 4:1, 5:1, and 6:1 ratios of clay to sand to mimic ceramic tempering. Tablets were analyzed in the lab using the same XRF procedures as the artifacts. Here's some photos of clay collection here. On the left here is a collection from the Terraton Basin, of the remnants of Lake Terraton. Here's the Big Lost River, cut of the Big Lost River. Here are some pictures of the tablets we created. And you can see the color variability among them from gray to dark gray to more brown clays. And we actually had a whole pottery day too, where we created pots out of all of these various clays, which was fairly successful. So a small X was etched into both sides of each tablet to mark the exact locations for XRF analysis. Each tablet was photographed and additional attributes were recorded both before and after firing, including color, length, width, thickness, volume, and mass. Mass was determined using an analytical balance with a readability of 0.01 milligrams. Since 3 tablets were created from each clay collection locality, one was fired at 650 degrees Celsius, one at 850, and one at 1050. More specifically, the tablets were placed in an electric kiln and dried at a temperature of 250 degrees for 1 hour before the temperature was raised to either 650, 850, or 1050 for 3 hours. The kiln was then turned off and the tablets were allowed to cool before being removed. Clay tablets were analyzed with an Olympus Vanta M series portable XRF spectrometer, equipped with a 4-watt X-ray tube, rhodium anode, and silicone drift detector. The instrument operates using a factory geochem mode that relies on a fundamental parameters calibration and a combination of 3 beam settings to optimize measurements of separate element groups in silica-rich materials. Each sample was analyzed in the exact same marked location for 180 seconds. That's 60 seconds per beam setting, in 2 separate spots, front and back, and the data from the 2 analyses were averaged. 13 elements are regularly quantified by the INL-CRMO for archaeological ceramics. Beam 1 measures manganese, iron, zinc, rubidium, strontium, yttrium, zirconium, and niobium. Beam 2 measures aluminum, potassium, calcium, and titanium. And beam 3 measures barium. The table to the right provides a summary of energy, current, and filter parameters for each beam setting. A check standard was regularly analyzed under equivalent conditions at the start and end of each analytical run to monitor instrument performance. The standard is SRM 2711A, a Montana soil. An SRM intended primarily for use in the analysis of soils, sediments, or other materials of a similar matrix. The table shown here reports average elemental concentrations for 23 analyses of the SRM 2711A standard, measured by the INL-CRMO relative to published values. To assess the impact of firing on the 13 elements of interest, analysis of variance tests were conducted as well as matched pair statistical tests, also known as paired t-tests. The ANOVA tests were used to compare the means of the unfired and fired groups by element to determine if there were statistically significant differences between them. While the matched pair tests were employed to compare the elemental concentrations of unfired clay tablets to tablets fired at the various temperatures, a matched pair test was also run to assess changes in mass pre and post firing. Matched pair tests are appropriate in this context because they analyze differences between two related measurements for the same object to see if statistically significant differences exist. Whereas an ANOVA assumes that observations within sample distributions are independent, matched pair tests do not, and thus directly test for differences for each case before and after a repeated measurement. All these tests assume a normal distribution for making comparisons, so Shapiro-Wilk tests were employed to test for normality. Be the ANOVA and matched pair tests, most distributions were normal. However, calcium distributions across all temperatures were not normal, and the aluminum distributions for tablets fired at 650 degrees was also not normal. A simple log 10 transformation was used to normalize the calcium data sets. For the aluminum distribution of clay tablets fired at 650 degrees, a single outlier prevented effective transformation and was excluded from the analysis. Non-parametric Kruskal-Wallis tests were employed to test whether or not there were significant differences in the elemental concentrations of untempered versus tempered clay tablets at various tempering ratios. All right, so let's get into the results here. So after firing, there was a notable reddening of the clays, particularly those fired at 1050 degrees, likely resulting from oxygen in the kill's atmosphere, causing metals like iron to remain in their oxidized state. This process of oxidation was not as pronounced in samples with higher concentrations of calcium, which I'll return to here. And you can see that this reddening in the samples at the top. There were also corresponding changes in the texture and hardness of samples, which, although not quantitatively measured, showed evidence of increasing hardness and incipient vitrification as temperatures increased. The matched pair tests for pre- and post-firing mass demonstrated a significant loss of mass across all firing temperatures. While on average, mass decreased 0.4% when fired at 650 degrees, this number increased to 3.5% and 3.8% at firing temperatures of 850 and 1050 respectively. To test the impact of firing on the elemental composition of clay tablets, an ANOVA test was first run to test for differences in the mean composition of tablets fired at the various temperatures. 8 of the 13 elements exhibited significant increases in elemental concentrations after firing. Calcium, manganese, zinc, zirconium, and barium did not exhibit significant increases according to the ANOVA. The firing of clay resulted in a statistically significant increase in the abundance of each of the 13 elements considered in the study using the matched pairs test, regardless of firing temperature. At 650 degrees, there was an average increase of 8.2% across the 13 elements of interest. Calcium increased the most at 9.5%, while barium increased the least. At 850 degrees, there was an average increase of 12.4%. Calcium increased the most, while barium increased the least. And at 1050 degrees, there was an average increase of 12.3%, with calcium again increasing the most and potassium increased the least. As firing temperatures increased from 650 degrees to 850 degrees, there was a universal relative increase in elemental concentrations ranging from 2.9% of niobium to 5.9% of yttrium. As temperatures increased from 850 to 1050, the pattern was not universal. There was a corresponding increase in the elemental concentrations of calcium, zinc, strontium, yttrium, zirconium, niobium, and barium, but a decrease in the concentrations of aluminum, potassium, titanium, manganese, iron, and rubidium. One other result of note is the impact of tempering or other inclusions in a ceramic paste that can impact data output. More specifically, as the percentage of inclusions in a clay matrix increases, there are corresponding changes in the elemental values obtained from XRF analysis. Increasing proportions of sand in a ceramic paste lead to dilution effects. In some contexts where ceramics are highly tempered with sand or other materials that do not significantly impact the elements of interest, these dilution effects may have a counterbalancing effect on corresponding increases in elemental values when clays are fired. Testing for and modeling such impacts deserve future attention. So for example, here, this figure shows rubidium measurements at different tempering ratios. If you look at BLR2, your rubidium measured for untempered is here, and they reduce as tempering increases. A question arising from that, right, is, are these differences significant? Using non-parametric Kruskal-Wallis tests, we demonstrate that there are generally no significant differences in the elemental values of any of the 13 elements at any tempering ratio with an alpha of 0.05, with the exception of niobium and barium at a tempering ratio of 6:1. This is unexpected because such differences were not evident for niobium or barium at the higher tempering ratios of 5:1 and 4:1, and one would expect higher differences in elemental values to exist as more temper is added to a clay matrix. This may reflect the low sample size and/or our sampling strategy, in that our sand samples were not pure sand and were not necessarily homogeneous. So turning to a discussion of the results, how do we explain the various phenomena we are observing? Why do elemental concentrations change due to firing? The first explanation is that there is a change in the mass fraction of the various elements in the sample, whereby the decrease in total mass of the tablet results in an increase in the abundance of a particular element. The second possible explanation is that the firing of the tablets is changing the matrix of the sample and associated attenuation rates for the elements of interest. We have already noted the increasing hardness and incipient vitrification of samples as firing temperatures increased. This is discussed by Coltrone et al. 2001, who note partial vitrification of carbonate-rich ceramics at temperatures above 900 degrees and significant vitrification at 1100 degrees. For XRF analysis, these are known as matrix effects, which are the practical issues resulting from XRF analysis of materials of different composition. More specifically, matrix effects relate to how X-rays react as they pass through a material due to a combination of absorption and scattering events, major factors that define the intensity of the final X-ray signal. Another point of note relates to soil moisture and the corresponding loss of mass. The firing of raw clays resulted in a significant loss of mass regardless of firing temperature, a phenomenon that's likely related to the loss of water and carbon. Water volatilizes at temperatures below 650 degrees Celsius, so it's not surprising that any residual water in the samples was lost, leading to a decrease in mass. Interestingly, prior studies have demonstrated that the presence of soil moisture can lead to an underestimation of elemental concentrations, which could in part explain the increase in elemental values after firing. This could also partially explain why we see increased concentrations of elements using XRF when Cogswell et al. 1996 observed no changes in bulk chemistry via NAA. The carbon present in clay matrices is often found as calcite or calcium carbonate, which begins to decompose at temperatures greater than 700 degrees and disappears above temperatures of 800 degrees. The figure here shows the relationship between the original calcium concentrations of the unfired tablets versus the corresponding loss of mass at various firing temperatures. At 650 degrees, the loss of mass remains fairly constant across all samples regardless of calcium content. However, at higher firing temperatures, those at which carbon volatilizes, there is a clear relationship between increased calcium content and corresponding decreases in mass. In this context, it's likely that higher calcium carbonate in clay samples results in a matrix more abundant in carbon, which is lost as firing temperatures increase. So turning to the archaeological relevance of all of this, the results of this study have pretty serious implications for archaeologists attempting to undertake ceramic provenance studies. And the following example illustrates this effect further. The figure here displays data obtained from XRF analyses of ceramic artifacts from 3 pre-contact sites in eastern Idaho, using the same instrumentation and settings as the current study. The results of this prior study highlight the existence of 3 geochemical macrogroups, A, B, and C, each with 2 subgroups within them that can best be distinguished using principal component analysis, hierarchical cluster analysis, and elemental biplots. By overlaying the current clay analyses with ceramic geochemical groups, it's possible to see how the firing of geological clay reference materials can have a serious impact on the conclusions drawn about possible provenance. This is specifically outlined in the table here, which documents the overlap of clays with geochemical groups based on firing temperature. The specific clay collection localities that overlap the geochemical groups are different depending on whether one uses the unfired samples or those fired at 650, 850, or 1050. While clays that overlap group B1 stay consistent across firing temperatures, the overlap between groups C1 and C2 varies considerably, which in turn could lead to differing archaeological conclusions. These issues can in part be mitigated by using elemental ratios to compare clay data to ceramic geochemical groups. To demonstrate this effect, match pair tests were employed using common elemental ratios in XRF analyses of archaeological ceramics to test the change in ratio values at various firing temperatures. The ratios included mid-Z elements like strontium to rubidium and zirconium to yttrium, and major transition metals like manganese to aluminum and iron to titanium. Interestingly, there were no statistically significant differences in elemental ratios between unfired clay tablets and those fired at the various firing temperatures. Depending on the archaeological context and the complexity of the data, however, it may not always be possible or appropriate to use elemental ratios. For example, in contexts where geological clays are derived from similar parent material or overlapping alluvial systems, elemental ratios may not differ significantly between compositional groups, independent of firing temperature. So what can we conclude from all of this? Well, the results of this study show that the firing of raw clays resulted in a significant loss of mass regardless of firing temperature, likely related to the loss of water and carbon. Moreover, the firing of clay resulted in a statistically significant increase in the measured abundance of each of the 13 elements considered in this study, regardless of firing temperature. This phenomenon is likely related to either changes in the mass fraction of the analytes of interest after firing and/or lower attenuation of fluorescent X-rays during measurement of fired samples due to changes in the matrix and loss of volatiles, chiefly carbon and water. The underestimation of elemental values due to the presence of soil moisture in unfired clays must also be considered as a potential source of error. Using an example from eastern Idaho, it's further shown that provenance assignments of ceramic artifacts can change based on the firing temperature of the comparative clay reference material. As such, we recommend that raw clays be fired before they are compared to ceramic artifacts, and specifically to temperatures that approximate the original firing temperatures of the artifacts under consideration. That said, these issues can in part be mitigated by using elemental ratios to compare clay data to ceramic geochemical groups, but this may not always be appropriate depending on the context. So here's some future issues to consider. It's not currently clear if these issues are unique to XRF, and testing these changes using other analytical methods may be required to determine whether the changes observed in this studies are real rather than apparent. Testing for and modeling the impact of temper deserves attention in the future, building on the work of Frahm and Ellery and others. Future studies may benefit from using pure quartz sand as a tempering agent and rerunning the analysis. While the addition of temper generally did not significantly impact elemental results, there's nonetheless evidence that the addition of sand still produces dilution effects, which suggests that at some point, comparisons between highly tempered ceramic wares and raw clay samples will not be valid. There are a wide range of complicating factors when analyzing ceramic artifacts using XRF, and the interpretive potential of such studies is greatly enhanced when combined with other analytical techniques. Petrography is a big one. When properly implemented, studies of this type have the capacity to make significant contributions to the discipline. There are many people I'd like to acknowledge throughout this work here, and of course, thank you all for listening.
Thank you so much. That was exciting. I'm happy to invite questions. Please be bold. I don't want to be the first again who has to ask something. Well then, if there are no raised hands, then here we go. I think I go for Kyle first. I'll leave you hanging there, Ellery. I found that very fascinating that you see really the differences with elemental composition. It makes sense that you're saying, okay, it can be related to the water loss. So even if we have a dry sample, the water that's still in there in the pores coming from your study, it still affects our measurements, right?
I would argue that it does. Yeah, and certainly it's tough to measure the water content specifically, but yeah.
The unfired samples you measured, were they also formed as the BRICS, or did you have them in a different form?
No, they were the BRICS, the same BRICS.
All right, just 4 prepared, and then we did the measurement thing.
Yes.
All right, then I take back the other ones I have, and I saw Nadia raised her hand, so yay, go.
Good evening. Just a remark about the differences of composition between unfired and fired ceramics, because I already had the opportunity to analyze some samples that were coming from the same workshop, ceramic workshop, Iron Age or Bronze Age or something, these periods, and it was not with pXRF, it was with WD-XRF, and we observed also differences. So it's not only a problem of even if it's XRF, but you know that for WD you prepare, you homogenize, you vitrify so there is a difference of composition due to the clays itself and the composition of the natural and especially for calcareous productions. And another insight I would like to share, it's with potassium, because I already observed also, it was in another topic when I was working on ethnographic ceramics, when we observed a decrease on potassium between unfired, because it was the case. I have the raw materials and the final product by the potters, and we observe a decrease on potassium also during the firing. So it's the volatile effect also of the. It was just to share two cases I already observed.
And I just wanted to clarify, the unfired samples were run and then they were fired and rerun again. So it's the same measurement as a repeated measurement on the same tile or tablet itself.
Yeah, it's different,
Yeah,
but it's maybe we can add.
Yeah, and the instruments are like as you pointed out with WDXRF or whatever, the instruments are doing what they're supposed to, right? We took a sample, we analyzed it, or Kyle, in this case, Kyle analyzed it, and then we changed it, and then measured it, and it was different because it changed. And so, yeah, this is again the kind of thing that geologists don't care about. We're kind of weird in what interests us, and that we're not subjecting these things to pressures and temperatures under the earth, and to make metamorphic rocks, but we're doing something else to them. And so, yeah, it falls on us to understand these kind of weird transformations. But yeah, the instruments are doing exactly what they should. Kyle, I missed a few? Sorry, did you measure loss on ignition between the two, just by mass, or between unfired and
by mass? Yeah.
Yeah. Okay. Cool.
Thank you. So, Iota, you would be up.
Thank you very much. Well, thank you both, the speakers, for these wonderful talks. I mean, it's amazing all the work you've done, but what is most amazing is the fact that it's so hard. XRF is just simply very, very hard method to interpret the data. And everybody seems to think that with a portable machine nowadays, with the ease of the equipment, with no background in sciences, they can just take a snap and just take the results and run or publish or whatever. I have two questions. That was my comment, because this is what we experience here in Greece. I am. Well, one question was for the first speaker, and I would dare to ask you, would you consider having the problem with calibration? I mean, it's a matter of fact. Have you considered to prepare somehow international standards that everybody can use? Why do I say that? Because in Europe, there was on metals, on XRF analysis, an inter-laboratory. So they would send the same set of standards to the other laboratory and run the analysis. And there was a massive difference between the results. Like for tin, for example, there was a plus or minus 5. So it either it has some tin or not. So it's so there is an established problem with calibration and the standards that we use. So if we don't share the standards, how can we possibly confirm the data that they're valid anyway? Because everybody uses their own standards and everybody uses their own setups. I feel anyway. So
Yeah. That's a great comment. Yeah, or question. Yeah, I mean, I would also point out that if you take 2 neutron activation reactors, they will generate numbers that are different too. So
exactly.
So yeah, again, it's one of those things where it's an inherent problem with anything. Why? So I would say that I think it's a great idea to do it with certified international standards. There's just a matter of coming up with what those are, and that sort of thing. And again, it's the kind of thing where, and I don't know what other labs are doing, but everyone was relying on, or so many. I mean, the standard geological calibration suite that every XRF lab at least in the US and probably elsewhere was using was those USGS standards. And then the guy retired and administration changed, and then suddenly like the whole page disappeared. If you didn't have like a saved copy of the certificates, you couldn't download them. They're slowly trickling back. There's a fraction of what used to be available now. So I would say the closest thing that there was to, a very commonly used suite of geological materials in XRF labs was suddenly unavailable. And so, this was, it's almost a bit of a stopgap, right? I don't anticipate, at least I hope not, in 30 years that I'm still going to be sending out BRICC sets. I would love for there something else to step up and fill that void. But and Kyle can chime in on me, at least in XRF of Obsidian, at least we all kind of coalesced around here is at least a check specimen or two that we can all kind of rely on. And in ceramics, just because there's an order of magnitude more people doing it, or 2 orders of magnitude, it was one of the things is when my students, I sat down to figure out like what's out there, what are people doing. People were either buying off the shelf things, or doing things like let's powder 50 kilograms of South African ceramics, archaeological sherds, and turn that into a one standard. But again, then now you have one standard. You can't determine how good things are with just one standard. So yeah, I would be fully happy if something stepped up and said, yeah, and I think that's going to be something that the community can push for more coherently, rather than just one person trying to do a stopgap that's again started off as I have students in China who have to use the equipment there. So how do we get the measurements we take at the Peabody Museum across the street to agree with those? And so it started out on a very, very practical sort of level. But yeah, I mean, there's certainly room for improvement. None of these are characterized as good as, say, that those shales that the USGS did. So yeah.
My question is, because several other colleagues, they end up using their own handmade kind of. So you've done an extensive amount of work, which would be useful to share to other labs, at least for those labs who deal with this particular kind of clay.
Yeah, and that's why I'll send as soon as one comes back. I've got 6 out on loan around the world right now, and as soon as those 6 come back, I've got people on the list to borrow them again. So
excellent.
Yeah.
Excellent.
And I think it also highlights the importance of matrix matched standards as well. So, Obsidian's a good example where you have the Mur, set of 40, where they're literally pieces of obsidian or other kind of rhyolites. Well, we're kind of playing with at the lab here is developing a calibration for other fine grained volcanics that are used for artifacts. And so all the USGS standards you get are powders. So trying to create a calibration where you might be mixing solid rock with powders creates some serious issues. And that's a good thing about the BRICC set. The matrix is not just powder.
Thank you very much. I see that Keelie has raised the hand, but I need to jump in first.
Thank you.
I'm so sorry. In regard to standards, there's a lot happening in the moment. Since we came together in the global pXRF network, we now know that there are much more standard sets out there, especially for pottery, than we knew before. So there's the one created, for example, by the former Mediterranean network pXRF Cannes, where Nadia was one of the leaders of, which also have created a standard set, which is now in 10 different laboratories across Europe. There's the BRICC set, and what we wish to do with the network when we can get the website running. So if you know somebody who can set up a website in Austria, let me know. We want to share where different sets are. We want to share which element width they cover, because as we learn, especially in the Caucasus, Ellery will know that, we have completely different composition of clays than we have in Central Europe, because different formation conditions. So one sample set alone doesn't cover all the variety, but having different ones, which you can use to intercalibrate, but also to build up. If I know in the BRICC set, there is stuff I need because it has the concentration of this element, but in Nadia's set, there's another, and Dept has one on spiked samples. So I feel there is a future coming if we get the opportunity to collect all this information, where we can see what's out there and then start to build from there. Also understanding who uses which international standard, because different producers present you with different standards to check. But that also means those using nitin in Central Europe, they will most likely have quite similar standards they use, because this is what the distributor gives you. So I also feel if we can collect this data all together, there's a good chance that we can start to build these calibration sets we wish for, where people can go and be like, I need this one, I need this one, I need this one. And we still be intercomparable if we can agree at least on a couple of standards that should always be there.
Yeah, I mean, I think this is this is the good problem to have when a technology, proliferates, right? And that, even when it was, again, back when it was a couple of, NAA labs doing this, like, for example, Harbottle never himself published the Ohio red clay analyses. It was just kind of like he had a card in his pocket or whatever where all the all of his values were and stuff like that, and everyone who had an NAA lab kind of knew it. But when you only have 3 reactors or on a continent or something like that, it's very easy to share standards, even though they still had their own standards. So it's one of those things where, like, if you look at what's been done in the past, you're like, oh, these 3 guys couldn't even get their act together and use the same stuff. That now that we have 300, again, it's a good problem to have that, that again, there will be some missteps along the way or some growing pains or whatever. But again, things like this group matter for, pulling things together so that, again, as we do weird things in archaeology. It's kind of up to us to study these things on weird scales and with weird amounts of precision and all that sort of stuff that other groups don't care about, because we're interested in teasing out the behavioral data, right? We can analyze a sherd down to the atom, and not have an archaeological question answered yet. And so, yeah, we've got these weird layers to our questions. But yeah, no, it's fascinating what people have talked about in the past with this stuff too. And it's funny how discussions keep coming back around.
Yeah, you know about that. Some things keep coming up. And Detlef also. All right, Keelie, we left you waiting for too long already.
No worries at all. I had a question for Kyle, if that's okay. So I was wondering about how you mentioned that the clay tablets you prepared, some of them had like very severe sort of color changes due to the sort of oxygenated environment of the kiln. And I was wondering if you had tried at any point to do like the same clay prepared and then in an oxygen-rich environment and then a reduced environment to see if that created some chemical difference as well that could be detected with XRF.
Yeah, no, that's a really good point. We did not do that. Jeremiah, who's in here right now, I think he was playing around with it kind of informally, creating a reduced atmosphere, and I think it turned black as I recall. But we haven't done any kind of formal measurements using XRF following that. But that definitely would be an interesting aspect of this as well.
Cool.
I tried a bit of that, trying to see if reduced and oxidized atmosphere on the same samples do create differences in my results. What I could see is that it does create differences in the fundamental parameter calibrations, especially if you have one that creates up to 100% values, because then the balance or whatever the part is that they call the unmeasurable part, this then increases if you have a reduced atmosphere. But that's the only thing that I really was able to see. I didn't really realize any increase in iron or whatever. So chemically, there wasn't much visible, but it wasn't a very big or elaborate study, so I wouldn't quite rely on that. But from the atmosphere, I didn't see much in the pXRF. Maybe
I think,
Ellery, you have different.
yeah, I mean, I think it would be really interesting. You'd have to find a way to do it really cleverly, is fire under reducing something with a good amount of iron, get a mass on it, and then, once it's at atmosphere and oxidizes, do you see, mass start increasing again as you're binding more oxygen, right? So that you're driving off water and maybe some carbonates are volatilizing, and then, you're left with iron with fewer oxygens. And then if you bring it into an atmosphere again, it should almost get slightly heavier again, I would think. I mean, you'd have to do with a lot of iron to get a measurable outcome. I'm trying to think, Kyle, you're not going to get titanium. There's not going to be that much other than iron. I mean, I guess if you're disrupting carbonates, then you have a lot more elements up for oxidizing. But I mean, I would think that the main driver in this should be the iron. Yeah. I mean, you're not going to change like titanium or something like that, or manganese or whatever. It's mostly going to be iron.
Yeah. Jutta, just jump in if you have a comment to what we're discussing.
Not necessarily on the black oxidation and reducing atmosphere, but on the differences that you would see on the different temperatures for firing. Perhaps one might want to think about the diffusion rates of the different parts. Because at different temperatures, you would have different diffusion rates for the different elements. So you would expect to see some of the light salts fluorescing almost in the upper part of the surface where the evaporation of the water happens, or below. That is at the drying rate, that you mentioned, and then some other parts would diffuse in a different rate, especially in the highest temperatures. So perhaps it's something to consider. That's all I wanted to consider.
Yeah, and I think it's an important distinction that might not have been obvious. I mean, it was there if I hadn't bored you yet. Was that, the difference between what I fused into, pellets essentially to send around, and what Kyle did is that I used a powdered shale, right? And so the heat and or any volatiles would have moved through that powder very differently than like a solid block or a tablet or something like that. So I don't think it's, incompatible that we only saw water loss and a proportional increase of everything else because we were using a powder and would have been very easy to drive the volatiles off, versus Kyle observing some differences between, a lot of elements went 3 to 6% higher, but some didn't. Some went in the other direction. I think that purely having the different original forms of these materials could easily make that difference. In your comment reminded me of that point.
Yeah, absolutely. The porosity would affect that, the diffusion rate anyway. So in the melt.
Yeah, and then it would have been heated more evenly and all that stuff. Because we clearly had convection going on.
But sorry, excuse me, I have too many questions. It's one question for the second speaker. Sorry, I miss your first name.
Hi.
And what was the plus or minus value for the trace elements in your machine? Because you would show us all the statistics and all that, but I missed that point. Sorry, you might have said that and I missed it.
The plus or minus, just what do you mean by that?
For the trace elements, because you would get a range, won't you? Of the repeated, how would you establish the repeatability of your method? You would get the plus or minus value, a range of values. Am I wrong in thinking this? I don't know.
Yes, for each one. And yeah,
For
I think
any trace element, not a specific. I don't have a specific in mind. I was just wondering if you showed us this, or
I did
if
not.
I missed it.
No, I did not show that.
Okay, that's all.
But if we're at data already, I was wondering, you use the Vanta and you use the geochem mode.
Yes.
It's a fundamental parameter.
Yes.
And it does calculate to 100%, right?
Yes.
Yes. Did you use the values the device gives you for the analysis you did? Or did you go back to the spectra and checked? Because if it does the 100% thing, maybe this also affects what you see. So it would be interesting to go back to the spectra and check if what you see in the calibrated data given by the measurement mode also appears in the spectra, just to be sure that it's not an effect of the algorithm that kind of try to compensate for something, as they make an assumption about what they expect and therefore do their calculation.
Yeah, no, absolutely. That's a good point. And
you might be able to see that. You might be able to see that in the LE.
Yeah, I was just going to mention exactly.
Yeah,
the LE measurement for that Vanta has a lot of there's a lot going on there that turning to the spectra is a good way of dealing with that. And we're kind of exploring that too in with CloudCal, with Lee Drake's CloudCal. It allows you to do a Compton normalization calibration with the spectra and kind of comparing that with the fundamental parameters output. It's really interesting.
Yeah, and thank you for the plug, so I don't have to do it.
Yeah.
And you also, with the newest version, you have the option to really optimize every element, and it doesn't have to be Compton. It can also be count rate, it can be time, whatever works best for the element. You can correct all the interferences, and you can use also your calibration data, so the measurements you've done on a calibration set like the BRICS, to do your own calibration and then check if your values you're getting are relatable to those that the geochem mode give you.
Absolutely, yeah. And that's the importance of the BRICC set here is really providing that that extra layer of calibration, I guess. But in a lot of ways, though, the fundamental parameters output has been very, very accurate, just based on your analyses of the check standards or that figure I showed. We're getting fairly good results based on a comparison with the check standard.
Absolutely, I have the same experience with the Niton and their measurement mode I was using there for years. That we also, just with the analytical data, so with the spreadsheet it gives you, under coefficient correction, we're really good. It's just now, more recently, that some of the things I feel are weird. And yeah, in the network with Nadia, comparing 10 different devices from different producers and different generations, that was one of the things that came up repeatedly, that we're not sure if the differences we're seeing are based on differences that are in the material or based on the calculations. And so now we're going back with Lee also to the raw data, because you can get it for all the devices now. So you can try it yourself.
Yeah, and my background is using a Bruker instrument, and so I've always been kind of weary of the FP kind of calibration routine. But the Vanta is very powerful, and it has the 3-beam settings, which allows you to get very accurate results for a wider suite of elements. And I've been very happy with it.
Yeah, it comes down to, some of it is just that I would say more recently, probably all the manufacturers are getting essentially pickier at how their own internal checks of the calibration are, right? So that if you go to a Niton 10 years ago, as long as their internal checks against the standard fell between a pretty wide range, a range that we would not be happy with, but that an economic geologist would be happy with, then it passed. And so I think it's that insistence that, hey, please do better, and that again, kind of these fifth generation instruments are really good. It's just, again, we're super picky in our weird mixed old rotten buried hydrated or not samples that we've got these sorts of things. I mean, this can go to other labs that were, I mean, here's the danger of like international standards again, but these powders, right? That the powders hydrate over time. A lot of them do. They're clays. Or their soils and stuff like that. And so if you look at the protocol, it's like, oh yeah, you have to dry it overnight before running it. But how many of these labs have had these powders sitting in the same analytical cups for a decade? And so sometimes you'll see people say like, oh, our values, especially for the light elements, change, over 4 months or something like that. It's like, well, is that your sample is hydrating, or is it your instrument was losing its calibration or something and then you're stuck, with trying to back interpret that. There's no way to really determine, okay, what did you do 15 years ago to make that sort of conclusion?
Yeah. You're discussing kind of powders versus bricks versus fresh breaks. I would be interested on your both's opinion to the effects that we have if we calibrate on the bricks or on other smooth surfaces and then measure on fresh breaks on the pottery. I know that there is in Germany the Frankfurt Pottery Sample Kit, where it's actually really measured on the fresh breaks to account for all those things that also happen if you have the rougher surfaces. What do you think? How important is it that we really measure also on the surfaces that we will be, or the same surface preparation that we will measure then in the field? And how dangerous is it to use a calibration based on something that is smooth or powdery than to the fresh breaks of pottery? If that makes sense.
Yeah, no, I think it makes sense. I would say, again, the Compton normalization that's in that FP routine is pretty good at estimating how much mass is in front of it. That part of the assumption is that it's flat, and so if it loses some signal, it'll try and adjust accordingly. I mean, the powders I don't like for exactly the reason Kyle mentioned. Is for a long time, everyone paid attention to just kind of the mid-Z sweet spot for obsidian and said there's not a meaningful effect, which is more or less true. But for obsidian, if you start looking at, I mean, the reason that my obsidian calibration sets don't have consensus values for titanium is that's when it went bonkers, and you could clearly see which labs were calibrating on powders and which were not. That as soon as you go lighter or lower energy X-ray, it doesn't have to be lighter on the periodic table, then the powders start to really matter. And so you have to go with something solid. And then, it's not an either or. I mean, can you, grooves on you might have to analyze something with a ceramic that has a grooved surface, then there's going to be an effect. I would say fresh breaks or fresh cuts are obviously the best. What you don't want to, what you have to keep in mind is, if you are grabbing sherds that were out of Minoan shipwreck or something like that. It's going to have seawater in it. It's going to be rough, and it's going to be altered. And again, the instrument's going to do what we tell it to. That's measure what's in front of you. It's just how much does what's in front of you correspond to what we want to know, and that is what was how does when this was made, its composition compared to the clay that you were made from. So yeah, I mean, it's kind of make the least bad compromise when it comes down to it. Is a lot of times if you have total permission to have a snippers or put fresh brakes on everything, do it. If you can have a tile saw in the field, do it. But if you can't, then you have to do your best. But yeah, powders are a problem, because not only is there the density, not only do they hydrate, not only can you not bring them into the field without the airline getting suspicious at you, you also have these thin films over the sample cups that break. You're adding a film to it as well. Something like a solid brick or a solid tablet like Clay made, like Kyle made, Clay, Kyle. Now your name is now Clay, Kyle. Kyle made, the more like it is, the better. And so that's why I don't have obsidian powders in the pyro set. I don't have clay powders in the brick set. And when I had powders, I turned them into not powders. So yeah, make the least bad compromise is really what it comes down to.
For the Vanta instrument, you definitely see it with the powders. That LE number just jumps when you compared to a solid sample. And with the geochem mode, it's measuring everything under magnesium, what we were told. So it's accurate. They're accurate numbers because there's the powders to different matrix, and so your lighter elements are larger.
Yeah. So it basically would be the worst case is use powder, better don't. If you have to, well, you have to live with a lot of difficulties. Then it would be something like the bricks with a smooth surface. But if you can get a standard set that is as close as possible to the sample preparation method you will use, that would be the best if it covers the elemental range you need. Correct?
Yeah. I mean, if you have to analyze powders, sometimes powders is what's left of ceramics. Then it makes sense to do powders or have some other means to adjust your calibration by knowing, hey, there's air in here, there's a thin film over it, and it is not physically the same thing as a solid hunk of ceramic.
Yeah. Thank you. Then I just have one question left on here. So that would be, when I started to do the analysis, I was told it doesn't really matter which, if it's a powder or a tablet or whatever, in which way I measure the clay, as long as I can see a correlation line between the clay composition and the pottery. For example, in silicone to aluminum, I can draw a line this way, kind of into the diagram. And I have the clays up there and the pottery down here. Then by taking out the silicium-rich parts, so the sand, by flotation or whatever, then I could still kind of say, okay, clays like that one, not exactly, but comparable to these, they could have been used very likely for the production of these pottery. So they are local, and the others that are far away from it, they are not. And of course, use the trace elements. So as Kyle was mentioning, that you could use ratios, but not always. Then could we try to combine it? Could we try to go with the correlation lines and the ratios and use that, even if we have the dilution effects from temper?
To me, I mean, the more kind of complicating factors that are added to something, that it becomes more complicated to make those kind of archaeological interpretations that are derived from it. It's such a particular, specific issue to XRF are matrix issues, issues that you just don't face with other techniques, and something that's, inherently difficult with just a heterogeneous material to begin with. So in my mind, matrix matching wherever you can is the ideal way to go.
Yeah. I mean, I would say if you're stuck with it, what I would do is, if I had powders, the artifacts have been turned into powders, and saying this is what you have to deal with. You can't do anything to them. Don't go and use them in your furnace, because they need to go back exactly as they are. How are you going to use your BRICC set now? Ha 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 ha. Right. So, what I would do, probably off the top of my head, is, try to prepare, those a few pieces of the bricks or the rocks that I have enough material and to a similar powder. And then with something like a discriminant function analysis, tell the software, hey, these are the same. Orient your axes and data analysis with the assumption that these are the same. Take out error that you can realistically get out of there. And then try some of the ones that I leave some of them out, see if they get plot right, test some of the standards as unknowns and see if they plot right. And then go from there. If that works, then apply it to the archaeological powders as being calibrated. It's a little similar to what I did when when we were trying to really press the size limit for measuring small obsidian chips, just tiny little retouch pieces, where now your mass estimates are getting off because they're not perfectly round, they're not perfectly flat, they're all these sorts of things. Is you are violating the assumptions, you're lying to the instrument. The instrument thinks that everything is perfectly flat, perfectly thick, and perfectly round, and you have lied by putting a tiny little chip on there. And the way to kind of get around it, to integrate those little chips into my reference materials, was, again, to jump into multivariate statistics and say all of these things are the same. Assume that there's something systematically different, and derive new equations, new axes to classify the unknowns as, and that worked. And so it's essentially, I'm proposing something similar here, is try and turn, if you're stuck with solids, try and turn some of them into powders, and rely on some heavy statistics to try and derive what's the same about them versus what's and minimize what's different between them. But like Kyle said, you start adding a lot more complexity to it. There's extra time and work and assumptions, and did you check the box to use words clustering or not? The more steps you put into it, the more assumptions and room for error. And so, like Kyle, and I've done exactly what Kyle has suggested before too, when back, in microprobe days, it's like, I'm just going to find a new standard that's closer to what we're dealing with, because the heavy lifting on the correction algorithms isn't cutting it in this scenario.
And I think somewhere there in there too, I keep going back to this LE number, but this is kind of issues we're exploring with this fine-grained volcanic issue we're facing, is an LE correction. If you can estimate the elements, from the, your oxides, if you can estimate the oxygen content in it and create a correction against it. It's something we're kind of looking into.
Yeah, that's a good idea, Kyle.
It's really fascinating what's happening in the moment. I just found the other paper. If it's fine, Ioannis, can I have one last one, please?
Okay.
One last question. Thank you. Or kind of a suggestion. Ellery, as you have been sending your samples around the globe, is there any attempt to collect all the data from the instruments and really make a big comparative study on the variability, on the way the values change between instruments, but also inside of an instrument? If you have one that has measured your BRICC set repeatedly, or the Paro, I don't really mind which one, more interested in the BRICS, surprise. But that would be something I would really be interested to see, just to understand better.
Yeah, there has been no such effort to see how much people have had to correct their values. I would say that, you know, sometimes, again, with some older machines, you know, like as people will send me data that maybe they haven't used, say, especially like an Obsidian Pyro set or something like that, and they'll send me the values, and I'm like, oh, yeah, I remember those calibrations in that year on that particular model. Like rubidium was often off by, you know, a factor of 1.8 or something like. I mean, again, that's just the, you know, the stuff that goes up there. No one has bothered to do that.
I would be really interested to learn a bit about.
Yeah, I mean, if someone wants to, I mean, again, this is, you know, again, the part of the reason that, again, it makes why I tried to publish everything and make it there is that, you know, ideally we'll be able to find everyone who is using this just by finding the citations. I mean, obviously I've got my list, but I'm expecting sometimes not much might come of it or something like that. But certainly I've got who's borrowed them and stuff like that. Every once in a while, someone will send me like a gob of data that will, you know, be like, oh yeah, here's what we did. But I would say, like Kyle, I mean, I've been doing this long enough. I think, you know, the first pXRF I used was like 2006. That was that like generation one. You know, by the time these new 5th generation instruments were coming out, it was almost like, why am I bothering to do this? These you know, these calibrations have gotten so good that, you know, in a sense, it's almost not for me. it's for students who are going off and using other instruments, or just doing it as we've established, you know, for good practice. That I might be happy with the data, but let's just, you know, do the right thing by showing how it's done, or we've done our due diligence.
Thank you.
Any more questions? I think you can straight communicate with 2 excellent speakers for more details. I think it's time to close now. So I thank you very much, both of speakers, because this time it was a very stimulating, you know, discussion. And it seems a little bit disappointing that we start from the beginning, but this is the good research which makes us be aware and cautious of how we are going on with the pXRF from now on. So I thank you once more. Thank you very much, the participants, and I hope the participants have gained a lot of information to be careful, you know, not pressing a button and getting results and publishing them. You can be very, very careful. And of course, it depends from the referees to cut such papers. I must say that. And see you in the next year, next round that we are going to hopefully to continue this interesting, you know, colloquia between the academy and the global XRF